We are discussing about this support vector machine, and in the last class, I discussed about the cases when the classes are linearly separable. Then, as you see that we are trying to maximize the margin of separability by defining a hyperplane, so that it maximizes the margin of separability. So this is an example where we will find that if the classes are not linearly separable, how this problem can be modified. Because the problem formulation, what we did, we assumed they are linearly separable. So if they are not linearly separable, then we need to modify this problem. And you take this example here, you can see by this sample particularly of the class, say of the class which is represented by these triangular shaped objects. It is being placed inside the region of, if I say the other classes, other objects of other classes. This is the example of an object of other classes. I already mentioned that if you can check the conditions of linear separability independent of classification by simply forming the convex hull of the point set, what has been given to you. And if those two convex hulls are intersecting, for example, in this case, we may consider, say, these are the two convex hulls, and you can see that these convex hulls are intersecting. So that's why you can say with the confidence that this is not linearly separable. So in such cases, how are you going to define this problem? How are you going to formulate the optimization problem so that you get a solution which will try to achieve try to maximally classify these samples, and also keeping these conditions of margin of the margin of separations are also in some way it is also respected. So we call it as a soft margin. So you will see that we can introduce another set of variables into our objective function in the optimization problem, and those variables will take care of this kind of deviations. So this particular diagram is trying to explain that part. You can see that this is the same kind of structure of classifier. That means you are considering a direction of classifier and then of the hyperplane, and then the hyperplanes in that directions which should be defined in this manner, that we have two hyperplanes, so that mostly all the data points of one hyperplane lie in one of its side, and for the other hyperplane will lie on the opposite side. So they are defined in this way. So in the positive side, the other hyperplane is the negative side. So that constraint of this greater than equal 1 and or less than -1, that gets satisfied. But this sample will not satisfy that condition. So this sample, so some of these samples, they will not satisfy, and we will be also, because if you would like to satisfy, then you won't get a solution. So you are allowing some of the samples not to satisfy. You are giving tolerances, but trying to keep them as small as possible, that number as small as possible. So we consider a variable, a slack variable. We name it slack variable, say S, for this sample. So each such sample is associated with a variable. Now, in general, every sample could be associated with a slack variable, but the value of those slack variables which are classified properly by keeping that conditions what we specified. So there it should be 0. Otherwise, the value would be a positive value. It should be greater than 0. So this is a slack variable, and which we are introducing, that example of slack variable, and then we call this hyperplanes marginal, I mean the hyperplane which are defining these margins, we call them as soft margin hyperplane. So once again, here also the the part of the objective function remains the same, because we would like to maximize the separation between these two soft margins. So which means we would like to minimize the norm of the norm of W, that is norm of the normal vector of the hyperplane, and also we would like to minimize the number of such deviated samples with this slack, using these slack variables. So if I say the sum total of the slack variables value should be also minimized. So let me so this is the new problem statement. That is the slack variable is incorporated here in the conditions, as you can see. Say here is the conditions where the slack variable is incorporated. So for some of the samples, you are allowing them to be greater than of a number, greater than or less than of a number plus. I mean, you can say these conditions. If I can ignore the effect of sign, if I just multiply with the class level, which is +1 and -1. So then I can say for some of the samples, we can simply say that they could be less than +1 also, and that reduction is captured by the amount, by the value of the slack variable, which is always a positive value, and you are trying to minimize the slack variable also. So let us see how this objective functions is redefined with these new constraints. So as I mentioned, that it would be the slack variables for every sample. The slack variable should be greater than 0, but if the slack variable lies within 0 to 1, then as you can see that though it is not satisfying the exact conditions of SVM, true as we defined the hard conditions, but from the testing point of view, still the sample is getting classified properly. But when the slack variable is greater than or equal 1, then actually the sample will get misclassified. So from the value of slack variable also, you can get some measure of your quality of your solution, like how many misclassified points are there in your solution, and how many samples are there which are in the overlapping zone, the non-separable overlapping zone, or I should say there are number of non-separable points, in that sense that there is certain kind of the convex hull is intersecting, but still you may get a particular so there are number of non-separable points. If ST is greater than 0, there are number of non-separable points, and then you have a soft error margin of this, which means you will not get a hyperplane truly separating them, but just using this slack variable concept, you can some of them you can identify. So the soft error is defined in this way. So you are trying to minimize this value, as I was telling you. The sum of this magnitude of the slack, or magnitude means the value of the slack variable, which is always positive, that should be minimized also, and that should be also taken considered when you formulate the objective function. So in the optimization problem, you have this new objective function where you can see this part is the same as same quadratic term what we have used in the previous case of separable classes. But this is the newly introduced term due to slack variable, and this is a constant. So it is taken as a constant for your problem. So depending upon, in fact, the value of this C, and this has to be a positive constant. So depending upon the value of this C, you you are trying to emphasize the contribution of this level. So the amount of tolerance that you are going to give, that also depend upon this particular parameter. So these are the no, constraints, new constraints which we are specifying with respect by taking into consideration of the slack variables for each sample. And right, so these are the new constraints. And C is called as the penalty factor. So same approach for constraint optimization approach. So you can see that the top function is a quadratic function once again, because still it's a quadratic term with respect to all those parameters. So so in the primary objective function, like here, what are the number of parameters? So in this function, what are the number of parameters now? Can you tell me? Which are going to be, with respect to which variables you are going to minimize this function? So I could see number of people, but no response. So Lokesh Chikula, are you there? Mehul?
So number of parameters are
what
two.
should be this number?
Number of parameters are 2.
How many parameters are there in this expression?
Sir, 3 sir total. 4. So there are 4 parameters.
I'm not able to get your, so can you increase your sound? Audio, I'm not able to get your audio.
So there are 4 parameters, sir. Am I audible?
Oh, just a minute. Yeah, sorry, Mehul. Tell me.
So there are 4 parameters.
Okay. Are you able to listen to my audio so far?
Yes, sir.
Because some of the microphone was a little outside. Anyway, so there are how many parameters you are telling?
4.
Why 4?
So W, T, and S.
You have not understood anything at all. You have not understood anything. Anyone else? Nitish Kannan. Piyali? Shreyash? I found a lot of people are not really attending classes. I mean, they are simply logging in. Anyway, so let me just explain that part. That, see, this is the weight vector. So we have considered the d-dimensional space. So there should be, you have this d number of parameters. Also, you have another parameter w naught here in the constraint. And then there are this slack variables. So which there are for every sample, n sample, there is this slack variable. So t is simply the index of the sample. So t is not a parameter here. So you get a number of
parameters. So you have so many parameters, n plus d plus 1 parameters here. And now if you're using, again, the Lagrange multiplier condition, so you have the conditions for satisfying, minimizing this slack variables. So this will come once again. See, and this is the condition that imposes ST should be greater than equals 0. So that condition is also there. So you should use another multiplier, Lagrange multiplier, for the slack variables. So this is what is coming into the primary objective functions. So that's what I mentioned, that simply to ensure that all slack variables are positive, you have to also put into the primary objective function for the unconstrained optimization, to make it an unconstrained optimization problem. And then solve for this new language parameters. So this is the primary problem. And as we have already discussed, how you can change it to a dual problem by making this problem as the minimization operations with respect to the, or maximization operations with respect to the Lagrange multipliers. So you need to satisfy these conditions. So these are the new conditions which you have to introduce the slack variables also into this constraint, and everything can be expressed in the dual problem, as you can see again in terms of Lagrange multipliers only. So so that makes the problem much easier, because now you are going to solve this unconstrained optimization problem, and which is also a quadratic quadratic function, quadratic convex function. So you can solve it. It's a quadratic optimization problem. It's not convex. It's a quadratic optimization problem. Quadratic means it's convex. Sorry. So it has to be subject to this, and then you can use the same quadratic optimization technique what you have used earlier also, and solve for support vectors where alpha t is greater than 0. So only you take the support vectors when alpha t is greater than 0. If it is less than 0, then you should not take it. Any question? And W naught, once again, you should take from the from those classes, from those cases, from those samples which are less than C, because that is what was one conditions here, as you can see here.
Sir,
yeah.
Sir, alpha t is the is Lagrange multiplier, because we want to, I mean, for the constraint that class level into WTXT plus W naught should be greater than 1.
Yeah.
And what is this mu t?
So this is also Lagrange multiplier to keep the constraint that all slack variables should be positive.
Oh, okay.
Right. So this is the range of alpha t now. Earlier, so range earlier alpha t could be any value, positive value. Now alpha t is also has a constant because of this new slack variables constraint, boundary condition. So slack variable also has to be satisfied this particular conditions, differential, if you differentiate with respect to that partial differentiate, it should be 0. So which shows that alpha t, to keep it positive and st positive, alpha t should be within this range. Okay. And so that is why when you are considering the conditions that, sorry, when you are trying to get W naught, you should consider only those samples for which you have alpha t is less than C. Not only greater than 0. Earlier alpha t, any alpha t greater than 0 will be considered will be considered that they are forming the support vectors, right? And you can take any of these sample and you can compute W naught. But now you have to consider only those samples whose Lagrange multiplier value should be less than C. Not only greater than 0, should be less than C. And you take average. And many of them will be 0. Many of them will be 0. So that was the case when we have nonlinear separability, or rather linearly non-separable training samples. And we discussed that how slack variables could be used. Now, there is one interesting trick that one can employ by converting a linearly non-separable cases to a linearly non-separable cases to linearly separable cases. So this conversion is that we can project the feature vectors into a higher dimension. So, for example, consider typical figurative demonstration that there are 6 samples, as you see, all triangular shapes. They are for class 1 and rectangular shapes are for class 2. So now we can project them, and it may cause separations in the higher dimension. All these phi 1, phi 2, phi 3, they are computed from the, they are functions of x1 and x2 in the feature dimensions. So given a feature vector, we can always compute the 3-dimensional point by computing phi 1, phi 2, and phi 3. And in a 3-dimensional space, if I get the scatter plot, it may happen that for those training samples, there is a hyperplane which is separating them. So that is interesting that we can convert the training samples which are linearly non-separable to a linear separable set in using this kind of feature mapping or this kind of projection to higher dimensional space. And then we can solve the same support vector classifier. We can use the same support vector classifier technique to get the linear SVM. However, it may happen that it may not be linearly separable also. So then there we can use those slack variable once again in that space also. But it makes the problem. We can see that it will introduce certain interesting feature properties in the class boundaries. At least you can get nonlinear class boundaries by doing this kind of mapping using those basis functions. So these are called basis functions. These phi 1, phi 2, phi 3. These are called basis functions. As you can see that this representation that this is the new variables z, and z is computed as a nonlinear transformation of the feature vector x. So all the components zz is the corresponding nonlinear function which is giving this component. So every component of z is a transformation nonlinear mapping from the feature space to that component only. And even that the use of W naught is also not in this expression, because you can always assume that Z1 itself is 1. So you can use this conveniently for the linear operations that we have mentioned. So finally, your discriminant function with this this basis functions phi jx with this transformation, it looks like this. And then your problem will be, as I have mentioned, that there is no guarantee for linear separability. So optimization problem would be same as considered to be the general case of linearly non-separable cases with this transformation also. So that means you have to introduce the concepts of slack variable, and you can see that here particularly you are using instead of directly the corresponding features, you are using this basis functions itself, that transformation itself. So here, if I discuss about the primal dual problem, so these are the solutions for that problem. So you can see that the dual problem is converted here, and in the same steps, following the same steps, and you are computing this term. Earlier, it was simply the dot product of two feature vectors, two feature samples, but now it has to be dot product in the transform space where I told you it's a mapping from usually lower dimension to the higher dimensional spaces. The interesting part is that this transformation could be made implicit. That means what is required to solve this problem is required to find out only this computation, this value only. So if I can get these values in some other means, I may not do directly this transformation for every feature vector. Now that saves me a lot of time, and also you will see that also saves me the problem formulation also. I mean that has given a different flavor of solution. So instead of performing nonlinear transformation, I will directly compute a function which we call kernel function. If you remember, we use this term kernel when we have discussed about this non-parametric method of Bayesian inferencing, and particularly k nearest neighbor classifications and other things. So it's the same concept of kernel here also we are using. We are considering the inner product of these two feature vectors there. So it is some sort of distance measure, and it has certain properties also. So we call it kernel function. And of course, the constraints, that constraint is also, will be also there, and also RT should be, alpha t should be within this range. So this is your discriminant function, and we call it kernel machine because finally you did not compute all the nonlinear transformation, etc. What is required? You require to define a kernel function, or sometimes we call it kernel matrix, because given the set of training samples, if you know the values for all possible pairs, and there are certain properties of this kernel matrix, it has to be symmetric, it has to be positive, and etc. etc. So those properties you need to satisfy. Then this problem can be solved, and you can get the discriminant function in this form. So this is a thing, and we call it gram matrix, and should be symmetric, and it should be positive semi-definite. So this is one interesting property of any matrix, positive semi-definite. Just to mention that, what does it mean? That it means that if you consider any feature vector, and if I take this particular computation, if I compute this thing, it is similar to a quadratic term with respect to this particular product, then these values should be always greater than equal to 0. Now, this is the positive semi-definite. If it is strictly greater than 0, then it is positive definite. Otherwise, it is positive semi-definite. So that is the property this kernel matrix should satisfy. Also, it should be symmetric. Right, and it needs to be provided when we do. And there are different kinds of vectorial kernel functions which are there. Like it could be polynomials of degree q. Say this is one kind of kernel functions. Here you can see that given two samples, any particular sample, you can compute it. Any two samples you can compute in this fashion. It could be radial basis function, and it could be Moholy-Nevus kernel function where S has to be given as a covariance matrix. It could be the distance function based kernel function. So there are so many different types of kernel functions that you can use, and you can solve this problem by using this kind of kernel conversion. There are also other kind of functions like sigmoidal functions, which is given by this. So one of the typical example of this solution, it just gives you the flavor that how the boundaries look like when you use this kind of kernel functions. If you use a quadratic kernel, which means consider this is the kernel function given to feature vectors, you can compute the kernel value by simply taking their dot product, and you do those things. Add it one, then square it. So the value what you get, that is the distance value or kernel value, or whatever I should say kernel value between these two, and those are used in solving the problem. So there you can see that effectively it is giving you a kind of parabolic boundaries and between the two classes. So because nonlinear. So it just shows here that the corresponding this operation, this is the nonlinear. Effectively, implicitly, you may compute this nonlinear transformation for every feature vector and perform the dot product, that would effectively give you the same thing. So that is how you are reducing your computations. You are not doing it, but it is effectively, this computation means you perform phi x, you perform phi y, and take the dot product. It is, you can see that if you expand this term, it is coming to the same thing. So that is the advantage of using a kernel function that you have. You can reduce your computation, you can make it much more simple. So, but as I mentioned, no need to compute this phi x. So to define a kernel, you can define also, you can learn this function. You know that is another kind of problem in this machine learning problem, that learning kernel itself is a problem. That what should be suitable kernel to design a classifier. Some examples of other kind of kernels. So it is not always that the representation has to be in the case of a numeric form, like in the feature dimension. It could be also defined notionally, like number of shared words of two documents, or edit distance between two strings, number of shared paths between two graphs, empirical definition of a kernel matrix on training sample. So empirical definition is, that's what I was mentioning, that you can have your own kernel matrix, which should be symmetric and positive semi-definite. So all these properties needed, I mean, all these conversions, they should satisfy that property. Then you can use it for designing a classifier using this concept of support vector machines using the kernel functions. So just to summarize what we discussed about support vector machine, that it provides the maximum margin based linear discrimination for two linearly separable classes. It generalizes to we can generalize it to a non-separable class by using slack variable, non-separable classes, and use of basis functions to map non-separable classes to separable in a higher dimensional space. So computation becomes simple and efficient with kernel functions, that we also have seen. Okay. So that was about support vector machine that we discussed. Now we will be discussing another interesting concept of this kind of linear discrimination classifier, and where we'll be taking help of logistic regression. So let us try to understand that. So we can understand this process if we again revisit our parametric methods of classification, where I mentioned earlier also that this could be made equivalent to a linear discrimination policy. You can derive a function which is also a linear discriminant function. So that part, once again, we will be visiting. It may be linear, it may be quadratic also. It is, but you can get a set of discriminant functions and use that policy to classify effectively. So what we are doing there, as you can remember, that in the Bayesian inferencing, we are trying to get the posterior probabilities of every class is given a data, and then assign that class which has the maximum value. So this posterior class expression itself could be a discriminant function there. So sometimes it could be linear, sometimes it could be nonlinear. So if I consider this case that your likelihoods are Gaussian, sharing a common covariance matrix sigma, and also there are but their means, their expectations are different for different classes. So then it boils down to be the functions which are determining these. I mean, maximization of posterior value means actually you are computing a set of discriminant functions and taking the corresponding class with maximum value. So the functional form, as you can see, it will be in this form if you use this Gaussian distribution we have discussed earlier also. You can see that prior term comes in the form of log of probability of Ci. So that is added, and the other term comes from the likelihood expression. So now let us consider that logistic regression setup that you need to understand a bit carefully. The other part was simple to understand. See, you consider the posterior of a class 1 given data x is y. So naturally, if the two-class classification problem, the other posterior value for the class 2 should be 1 minus y. Now, your classification policy could be any one of this. So either you can choose C1 such that y is greater than 0.5, which is mainly saying that this is the maximum out of them. Or if I take the ratio of y by 1 minus y, then it should be greater than 1 is the equivalent. I hope you understand that, because no, y has to be greater than 1 minus y. That is the maximum principle of posterior, and also for the discriminant function also you can see. Then if I apply logarithm operations of the last inequality, then you can see that log of y by 1 minus y should be positive. Now this function log of y by 1 minus y, it's very interesting function. We call it in a functioning form as a logit function. You might have heard this term. You will be hearing this term very often if you're working with machine learning subjects. And so it's a very very simple definition, but you need to understand this definition. So it is logit y means log of y by 1 minus y. Sometimes we call it log odds of y. So this is just the repetition what I mentioned in the previous slide. Now, if we have two normal classes sharing a common covariance matrix, as I mentioned that your discriminant function becomes linear function, so your log odds also become linear in that case. That you can show. Because that g1x minus g2x, when you have two linear functions, you can also express it into a single linear function. So there you can show that this logit would be also W transpose X plus W naught. So you understand this particular expression. So to explain this, which means as I was mentioning that this is W and this is W naught, because it takes care of the difference between two discriminant functions from the posterior functions. So you are considering difference between these two, and then if you apply the log operations, you will get this. So if equivalently it is giving this. One of the interesting thing is that inverse of logit function, also called sigmoid function. That is another function you will hear soon, because in neural network this is one of the favorite nonlinear function which is used, a popular nonlinear function. And here the definition, functional definition, is given to you. I hope you understood this functional definition. You see that logit inverse of y is 1 by 1 plus e to the power minus y. So that you need to understand. So y can be replaced here, W transpose X plus W naught. For parametric 2-class classification, what we can do here, same method, and you can see implicitly in the background the theory is Bayesian inferencing, but for explicit computations it looks like linear discriminants what you are deriving. So you estimate the parameters, you get the covariance matrix, you get the means of two classes, and then you compute the coefficients of gx, that is W and W naught, using these parameters as we mentioned. And while you are doing testing, simply use them. That's all. So this is a simple method of parametric method using discriminant functions. Or what you can do, you can use these logit concepts. That means you can compute to the posterior directly by y by 1 plus. You can see that your gx, this term is converted, used here. See, this gx is nothing but, right? So you are computing posterior here directly. Here you are not computing posterior, you are simply computing the sign, and that's all of the discriminant functions. But here you are computing the posterior with this model. And then if you find you can assign C1, then you can then use the same policy what we discussed. So this is the logistic discrimination of two classes. And there we'll see that using logistic regression, we can estimate this posterior probability. We'll come to that. So ratio of class density models can be, this is a ratio of likelihoods. And you can use log likelihood ratio is linear. That means true to normal density function. So this is a log likelihood ratio. I hope you agree with me. And if I consider the logit function, you can see logit function can be written as log of this. No, this is a log ratio of log odds ratio of these posterior probabilities. This is the logit function. Just to give you, if you say if this is y, you know what is logit function? What is logit of y? It is log of y by 1 minus y. Okay. So what is 1 minus y here? It is probability of C2 given x, because if y is probability of C1 given x, then that should be probability of C2 given x. And you can expand it in this term. As you can see, this is the log odds ratio, and this is the likelihood, this is the prior ratio, log prior ratio, and this W naught prime. Finally, it was, as I was mentioning, that your posterior can be computed as the in this form, in the sigmoid form, sigmoid of the corresponding logit values. So that is the relationship, that if you can understand this, then understanding the logistic regression becomes simpler. So in this case, the problem is that now you have a set of data, level data. Once again, two-class classification problem. Levels are given by this notation R, and you are trying to compute posterior directly, and you are considering it's a Bernoulli distribution. That means if y equals to probability of the class 1 given x, then 1 minus y should be probability of class 0 given x. So this is a Bernoulli model, and you are directly modeling them. So if I consider the likelihood of the weights with respect to given data, which means we are trying to maximize the corresponding probabilities of all these posteriors of the observations. So which can be given by these standard distributions we have already seen. Now independently they are occurring, so we can write in this form. And if I take the so we can define the maximization of log likelihood, which means the minimization of this minus log L, and then this energy function can be defined as in this form. So you have to minimize it. So you can see that this y's are here actually parameters. Y are not given. Y needs to be computed, to be estimated, whereas R is the level that is given to you. Okay. But y is related with x by that sigmoid, by that logistic function, where w naught and x, they relate y. So that is what we'll be using in the discriminant while estimating these parameters w's using logistic regression. So one of the method that we'll be using, once again, this optimization problem, we'll be using the gradient descent technique, and this just to show you the mathematical trick of getting derivatives of a sigmoid function, we can express it again in terms of its output. So that functional derivative can be expressed as the function of that functional value itself at that point. So which is y into 1 minus y. You can check it. You can do these operations, and you can prove that actually the derivative of y with respect to the corresponding variable x or a here is actually y into 1 minus y. So this is you can use in the expression of minimization of this energy with respect to every weight component, and then you can simplify this gradient computation as if it's a very familiar form. You will find this term, this kind of form, in many learning problem. You can see that this is the term, this is the input value of that particular jth component, and this is the difference from the desired level, what is the ground truth given level, and this is your probability. This is the soft probability of that class. It could be between 0 to 1 only. Since here the class levels are 0 and 1, you remember that. It is not plus 1 minus 1. This context we'll be using when you are using probability, then class levels are 0 and 1. So, so this is how numerically you are simplifying all this. You are taking care of all those, interpretations. So these are the two, gradients. So you can update weights using this gradient value, applying the same gradient descent technique. So finally, the algorithm will look like this. So you can assume some initial weights, then you can compute the corresponding posterior using that weight. I told you that posterior computation is sigmoid function of this value only. Then compute gradients, then update W and W naught, and you continue till you get the convergence. And you can extend it for multi-classes when you use this softmax function. You will find this particularly, this is used mostly in deep learning cases, so or in the neural network cases now in the learning. So the softmax, what you are computing, you understand that with this respect, you are computing the posteriors there. That is the mapping, and this should be your likelihood computations. So with this, let me summarize this particular topic, what we covered under linear discriminant functions. That discriminant functions we can explain also in the context of Bayesian inference. We see that last part of my lecture is basically it is explaining that how Bayesian inference is also involved in this case. It could be also explained by geometry. That is another interesting thing. And weights of the function to be learned by minimizing an objective function. That means that function, usually it is error due to misclassification. You can use gradient descent method. You can use stochastic gradient descent method, where I mentioned about this single relaxation single sample relaxation technique, methods of weight updation. We have discussed about SVM linear, also the SVM with nonlinear, non-separable classes. That is also linear SVM form. And another case where you can use the kernel matrix to get nonlinear boundaries. And finally, we discussed about logistic discriminations where we can get posterior directly from the level data.